Okay, this is the Unit 910 review, and we are not quite finished with Unit 10, but my seniors' finals are coming up next week, so this is the review for the senior final. And I'm going to have everybody take this final, even if you're not a senior. And then juniors, you have one more section that we're going to throw in, and then I'll test you on that stuff too. All right. But right now, let's focus on getting the seniors through their senior finals so they're ready to go to college and take calculus and all kinds of cool courses. So, in this test, when appropriate, give angle measures to the nearest tenth of a degree and lengths of sides in simplest radical form or to 3 significant digits. And that also, we'll do the same thing with area. Number 1, the sides of an isosceles triangle have lengths 5, 10, and 10. So the first thing I would do is draw a diagram, and I'm just going to draw an isosceles triangle. It's not the scale or anything, but rough it out and then let's label. So it looks like the base would be the 5, and then the 2 congruent legs would be 10s. So there's my diagram right there. Not perfect, but it'll get the job done. Now, what are the measures of its angles? All right, well, when we did problems like this, we were in right triangle trigonometry. So let's do it at first with right triangle trigonometry. Okay, so I'm going to go ahead and label my vertices A, B, and C, but again, you could label them whatever you want. I'm just communicating. And if I'm going to use right triangle trigonometry, I'm going to need a height right here. And do you all agree that that isosceles triangle right there, if I put in this segment for the height, I'm going to have 2 congruent right triangles? And that leads to the right triangle trigonometry that I can use to find the angle measures. So let's start with, well, if the base of this isosceles triangle is 5, then the distance from vertex A to the center right there would be 2.5. And then I have a side adjacent to angle A and a hypotenuse, so adjacent to hypotenuse, SOHCAHTOA. Isn't that going to be a cosine? So let's just go cosine of angle A would have to be the trig ratio 2.5 to 10. And you could reduce that now if you want, but we're going to use calculator, so it doesn't matter. It's hard for me to write this, but I'm going to go ahead and go 2.5 to 10. All right, if you want to go 1/4, please do. All right, and now, well, how do we solve for A? Well, we have to undo the cosine, so we're going to go inverse cosine of both sides. So this implies the measure of angle A would be approximately. Now get your calculator out and make sure you're in degree mode and punch out inverse cosine of 2.5 over 10. Okay, I did that and I got 75.5 degrees. So angle A there is 75.5 degrees, and I hope you remember the base angles of an isosceles triangle are congruent. So that means angle C would also be 75.5 degrees. And then by the triangle sum theorem, you also know the measure of angle B up there. So the measure of angle B is approximately, by our old triangle sum theorem, what do the 3 angles of any triangle have to add up to? 180 degrees. So I'm just going to go 180 minus the 2 75.5 degree angles. Minus 2 times 75.5 degrees, and that's going to be approximately, well, let me see, that would be 180 minus 151, which would be 29 degrees. And I wrote that 29.0 degrees to round to the nearest tenth. If you put a 29 degrees right there, I'd give you full credit. And that's how you do that with right triangle trigonometry. Now, I did mention, and you guys are experts at the law of cosines, and so could we have also found all 3 of these angles using the law of cosines? Let's give it a try right here again. So side, 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 and side, side, side implies law of cosines. So let's write down the law of cosines when we're looking for an angle, and our general formula is cosine of angle C equals a squared plus b squared minus c squared over 2 times a times b. All right, well, let's put in our numbers and see what we get. So that would imply cosine of this angle C right here would be, and remember, the A and the B are the sides that are adjacent to the angle we're looking for. So I'm going to call the A the 5, and 5 squared would be 25, plus the B then would be 10, and 10 squared would be 100, minus the C, which is the side opposite angle C, which is 10, so minus 10 squared minus 100, over 2 times, and then I go A times B right here, would be the product of my adjacent sides, 5 times 10, 50. All right, and that equals, looks like we can simplify this pretty easily, is that 25 over 100, or 1/4? I am going to simplify that one. So now, cosine of angle C is 1/4. Does that sound familiar on the way we did it? Didn't we get a 2.5 over 10? So I'm going to go then. The measure of angle C is approximately, and again, inverse cosine of 1/4 is 75.5 degrees. So if angle C is 75.5 degrees, by the base angles theorem for any isosceles triangle, angle A would also have to be 75.5 degrees, and then by the triangle sum theorem, angle B would be 180 minus both of those angles, which would give us the 29 degrees right there. So that's the same problem using the law of cosines and then a little geometry. All right, and remember on the previous slide when we used the right triangle trigonometry, we've got the measure of angle A, 75.5. Where's my arrow? There it is, right there. The measure of angle B, 29.0. Yep, measure of angle C is 75.5 degrees. Which brings me back to my college days. I had a math professor, probably the greatest professor I ever had the opportunity to take classes from. And his name was Brother Bill Fuller, University of Portland. And Brother Bill Fuller would always tell me, there are many roads to the ultimate reality. Okay, Brother Bill Fuller, University of Portland. All right, and what he was saying was that when you get into advanced mathematics, there's no just one way to do any problem. All right, you see, we just did number 1 with the law of cosines. All right, and then we also did the same problem with right triangle trigonometry. All right. And I don't know which method was easier. Probably maybe the right triangle trig on this one. But, if we're dealing with triangles that are not, isosceles, like a scalene triangle, and we have side, 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 we would definitely need to be doing the law of cosines. Okay, number 2. At a distance of 100 meters, the angle of elevation to the top of a fir tree is 28 degrees. So the first thing I'm going to picture is my fir tree. There it is right there. And then out here somewhere, I have an angle of elevation to the top of the tree of 28 degrees. And they want to know, how tall is the tree? So what's the height of this tree right here? So let's just create a right triangle in this diagram, because we are doing right triangle trig, and this is a 90-degree angle right here. All right, and this acute angle right here is 28 degrees, and the distance from the vertice to the base of the tree is 100 meters. So let's put that into our diagram. There's my 100 meters, and there's my acute angle of 28 degrees. Now, right triangle trigonometry. I'm looking for the side opposite my acute angle, and I'm given the adjacent to the acute angle. Let's see, opposite to adjacent, SOHCAHTOA. Isn't that going to be a tangent of 28 degrees equals the trig ratio of the height of that tree to 100? Now, in one step, we can solve this. Let's multiply both sides by 100. So h is approximately, and again, I'm just going to punch out 100 times tangent of 28 degrees. 100 times tangent of 28 degrees, and I got, and remember, this is going to be a distance, so we need to take this decimal answer and round it to 3 sig digs. That's going to be 53.2. And do I have units in this problem? Yeah. The height or the distance is in meters, so this would be 53.2 meters. and that's number 2. Okay, number 3. Oh, this is a great problem because it brings in the area of a triangle given your side angle side. Okay, so a regular pentagon, we'll go back to geometry. Remember, a regular pentagon is a 5-sided figure that is equilateral and equiangular. It looks something like that right there. All of the interior angles will have the same measure, and all of the sides will have the same measure. And this is inscribed in a circle. So inscribed in a circle, that would look like that. And that circle has a radius of 4. So let's just find a point at the center of our circle and put in a radius of 4 units. Just like that. Okay, now, how are we going to find the area of this pentagon with this information? Well, let's put in a few more radii into this diagram to create congruent isosceles triangles. So we're going to use congruent isosceles triangles and area given side angle side. And you're going to see what I mean in just a second. Do you agree that each of these segments would have to be 4 units as well? Because those are all radii of that circle. So that's a 4 right there. And now if I knew this angle right here, this interior angle of a side angle side, I could find the area of each of those triangles. So what do you guys think the area is right here? Well, is it one complete revolution 360 degrees? And how many triangles make up that 360 degrees right there? How many of those angles? 1, 2, 3, 4, 5. So let's just go 360 degrees divided by 5, and that equals 72 degrees. So each of these angles in this diagram, 72 degrees here, 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 and here. And those 5 angles would be 360 degrees. So now I have enough information to find the area of any one of these congruent isosceles triangles. So I'm going to say the area of the entire pentagon would be 5 times the area of this isosceles triangle right here. So I'm going to say uppercase K equals 5 times lowercase k, and that means area of the whole pentagon equals 5 times the area of those 5 congruent isosceles triangles. And how do we find the area of a triangle given side angle side? Okay, well the formula is K equals 1/2 A times B sine of the included angle C. Okay, so let's find our entire area right here. So the area of the pentagon would be 5 times, and then the area of each triangle would be 1/2. A times B would be 4 times 4, or 16, sine of, and what did we say that angle is right there? 72 degrees. So let's just punch that out on a calculator. You might simplify a little bit if you want to. All right, that is approximately. So you see what I did? I went 1/2 of 16 is 8. 8 times 5 is 40. So I just put 40 sine of 72 degrees. And I'm getting 38.0, okay? And that is the area of the entire pentagon to 3 sig digs. So 38.0, and do I have units? Well, my radius is in inches, so this area would be square inches. And there you go, number 3. Great problem. All right, number 4. Find the angle indicated. Be alert to problems with no solutions or 2 solutions. So, notice how I drew this triangle and it's not quite close because I am not sure with this information if I'm actually going to have an angle P right here. Because if you look closely, they give me a side, and an angle. All right, so see the P is 5. Notice how I put that 5 opposite the angle P if the angle P exists. And the Q is a 4, so that would go right here, opposite angle Q. And then they said angle Q is 74 degrees, right there. Now, will this create a triangle? All right, well, remember, this is side-side angle. And with side-side angle, All right, I've got to realize that I might not have a triangle at all there. Angle P may not exist, or I might have one right triangle, or I may have two triangles, one acute and one obtuse. Okay, so let's find out. Side-side angle implies law of sines. So law of sines it is. So I set up my ratio. And I'm looking for angle P, so I'm going to start with a sine of P over the side opposite of angle P, which is a 5, equals sine of the angle I know, sine of 74 degrees, over the 4. All right, so let's try to solve this for P. So the first thing you would do is multiply both sides by the 5. So I'm going to say sine of P then equals 5 times sine of 74 over 4. Now, that 5 over 4 right there, this may be a number greater than 1. So let's check that out. All right, 5 sine of 74 over 4. Okay, so 5 sine of 74 divided by 4 is 1.20 approximately. And if sine of P equals 1.2, well, remember sine oscillates between 1 and -1. So if I did inverse sine of that 5 sine of 74 over 4, my calculator would give me an error. So this tells me that angle P does not exist. Okay, so that was be alert to problems with no solutions or two solutions. This was a situation where we have no solution. Angle P does not exist. All right, now B, they just gave us a little bit different information here. So this time they told us the P is 9, so that would go right here. And the Q this time is an 8, so that's going to go right there. And then they're giving us angle P, 23 degrees. I know that I wrote that as a broken triangle right there, but I also put not to scale. I'm just using the same diagram right here. And this time they want us to find angle Q right here. So side-side angle, law of sines. So let's go sine of the angle we are looking for, sine of Q, over what's opposite that angle Q? 8. And that equals sine of the angle I know, sine of 23 degrees, over the 9. Okay, now let's multiply both sides by 8. So sine of Q equals 8 times sine of 23 over 9. Now that 8 over 9, then the sine of 23, I think this one's going to work. So what I'm going to do is I'm just going to solve for the angle Q right now by doing inverse sine of this entire right-hand side. So the measure of angle Q equals, now look at how I punch this out, and always check inverse sine of 8 sine of 23 degrees divided by 9, and let's see what our calculator gives us. That's going to be, and that's an angle, we need this to the nearest tenth, 20.3 degrees. Okay, cool. Now, remember side-side angle too, you've got to check, would an obtuse angle work for angle Q? And I know it's drawn like that would have to be acute, but maybe I didn't draw it. Remember, this is not the scale, so I've always got to double check for two solutions. So I'm going to break out my unit circle right here, and I'm picturing the 20.3 degree angle. I don't know, right in here somewhere. All right, so sine of Q, sine of 20.3, that's positive, right? And now, isn't sine also positive here in quadrant 2? So I could have this terminal ray right there, creating this obtuse angle right there. And wouldn't this obtuse angle right here simply be 180 minus 20.3, which would be what, 159.7? Right there. So there we go. There's my second possibility. But I hope you notice I put that in black because you always have to check. Look at the given angle, 23. Can I have an angle of 23 degrees and 159.7 degrees in the same triangle? No, because the sum of those two angle measures would be greater than 180. It wouldn't work. So our only answer is the 20.3 degrees. So when they say be alert to problems with no solutions or two solutions, you just found a situation in 4A where we had no solution. And then 4B, a lot of people would think this 159.7 is going to work and you have two solutions, but 159.7 degrees does not work with that 23 degree angle. So there's only one solution here. Okay. Now, observers at point A and B 30 kilometers apart. Well, let's draw that. So here's point A, here's point B, and that distance is 30 kilometers right there. They sight an airplane at an angle of 40 degrees and 75 degrees respectively. So I'm going to put an airplane up there in the sky, and now I'm going to create a triangle right here. Okay, and could I call angle A the 40 degree angle and this angle B the 75 degree angle? There we go. All right, so that's what they've given me. Now, how far is the plane from each observer? Okay, well, we're going to have to find this distance and this distance with some trigonometry right here. And now, remember this too. Do you have enough information in this diagram right here to find this angle up here? So, angle, side, angle. I see two angles there. I'm going to try to use law of sines. All right. And this angle by the triangle sum theorem would have to be what? 180 minus 75, that'd be 105. Minus 40 more, that'd be what, 65 degrees right there? 65 degrees. All right, and now I have all the information I need right here. Okay, so here's what we're going to do here now. This side A right here, okay? Well, law of sines. I'm going to use the reciprocal version because I'm looking for side A, so I'm going to set up the proportion of my A over sine of the angle opposite the A, which would be sine of 40 degrees, equals, and then what do I know? Well, I know the 30 kilometers over sine of the angle opposite 30 kilometers, which would be 65 degrees, and now I can solve for A in one step. So A is going to be approximately, and aren't we just going to multiply by sine of 40 degrees? So my calculator, I'm going to go 30 sine of 40 degrees divided by sine of 65 degrees. And my calculator gave me, and this is a distance, so I need 3 sig dig, so that would be 21.3. And do I have units here? Yes, this is in kilometers, so that would be 21.3 kilometers. Okay, that plane's up there a ways. All right, now let's find side B right there. Now we're going to do exactly the same thing, except now we're looking for B, so let's go B over sine of the angle opposite the B, which would be 75 degrees, and then equals, and let's use the same, 30 over sine of 65 degrees. Now this time, to solve for B, we're just going to multiply both sides by sine of 75 degrees. So I'm going to get 30 sine of 75 degrees divided by sine of 65 degrees. And that one should be a little bit longer than the previous one. Let's see how we did. Yeah, look at that. 31 point, well, that's going to be a 0. So is that 32.0? 32.0. And one more time, what's my units? Kilometers. And there you go. Now, some people might see this problem a little bit differently and get two very different answers that are correct. Okay? And again, I picture the plane somewhere in between A and B, but some people might picture the plane out here. All right? And that would change up the diagram a little bit and give you two totally different answers. So another viable solution to this problem would look like this. Now, I'm not going to go through the whole thing, but see the 30 kilometers right here, but the plane's over here. And there's my A, and there's my B. That's all the given information. People just are seeing this a little differently. And with this one, they got A is 33.6 kilometers, and the B is 50.5 kilometers. A very different answer. It's just how you see it. Okay, number 6. A triangle has sides of length 5, 8, and 10. So that's a scaling triangle. I'm just going to draw a rough sketch of a scaling, not to scale or anything, just a scaling triangle. And then it looks like this is my smallest side, so I'm going to call that a 5. And it looks like this would be my middle side. I'm going to call that an 8. And then my largest side right here is the 10, right there. Okay, so there's my scaling triangle right there with all the given information. Now, what is the measure of its largest angle? Okay, well, from geometry, you should know that the largest angle would be opposite the longest side of the triangle. So that would be this angle right here. And we're going to find that angle. Largest angle is opposite the largest side. So let's just call that angle a measure of x, and let's solve for x. And then what do we have right here now? All right, could I use law of sines right there? Could I go sine of x over 10 equals? I'm going to have to use law of cosines with the side, I think. So side, law of cosines, all right? And we're looking for an angle, so we're going to go the cosine of c equals formula. So let's write this one more time. Cosine of angle c equals a squared plus b squared minus c squared over 2 times a times b. All right. Now let's put this formula in perspective of this triangle right here. So this x, this measure right here, is that c right there. So I'm going to say cosine of x equals, and you know the a and the b are the sides adjacent to the angle you're looking for, so that'd be a 5 and an 8. 5 squared, 25, plus 8 squared, 64, minus the c squared, that's opposite my angle, that's minus 10 squared, 100, over 2 times a times b. And again, a times b would be 5 times 8, or 40. All right, so let's go. X is approximately, and again, you know, you could just take inverse cosine of this entire thing right here. All right, or you could simplify a little bit. So I went inverse cosine, and I just wrote it the way I saw it. And make sure that you have parentheses around your numerator. 25 plus 64 minus 100, and then divide by the, and I would not go 2 times 40, I would do the 80 right there. All right. Now, what do I get here? That's an angle, so that's going to be 97.9 degrees. And there you go. That's the largest angle in that triangle. Now, was my drawing perfect? I don't know. That looks like I drew it a little less than 90 degrees, actually. But again, you label everything, and your drawings don't have to be perfect. All right. 2 hikers follow a trail that forks. So I'm visualizing right now they're at a fork in the trail. There's my fork right there. Each hiker takes a different fork. Not a good idea in the woods. And the forks diverge at an angle of 67 degrees. So that means this angle right here is 67 degrees. And both hikers walk at a speed of 3.5 miles per hour. And the question is, how far apart are the hikers after 1 hour? So if this hiker is walking at 3.5 miles per hour for 1 hour, yet 3.5 miles here, and also the same here, 3.5, and they're asking us for this distance right here. How far apart are those hikers? All right. Well, I see side angle sides, so I'm thinking I need law of cosines again. All right. And I am looking now for a distance. So my general formula is going to be c squared equals a squared plus b squared minus 2ab cosine of angle c. Just like that. Now, let's put that in perspective of this triangle right here. And remember, C is the side opposite the angle we know, the included angle. All right, and we're calling that D here. So I'm going to start with a d squared, and then the a and the b are the sides adjacent to the included angle. So that's going to be a 3.5 squared plus another 3.5 squared minus 2 times, excuse me, 2 times a times b, or 3.5 times 3.5 cosine of the angle C, which we know that angle is 67 degrees. Now, to find that distance, all I'm going to do is take the square root of both sides of this equation. So d is approximately, and I'm going to break out my calculator and do this very carefully. So I went square root of, instead of going 3.5 squared plus 3.5 squared, I did 2 times 3.5 squared minus, and then 2 times 3.5 times 3.5. I went 2 times 3.5 squared, cosine of 67 degrees. Now, I could have typed it exactly the way you see it right there, but I wanted to condense it a little bit too so you guys could see it on my PowerPoint presentation. And when I punch that out, I got that, and that's a distance, so I need 3 sig dig, so that looks like a 3.86. And do I have units here? Yes. They're walking at a speed of 35 miles or 3.5 miles per hour, so that would be miles right there. Okay, number 8. When only 3 parts of a triangle are known, like we've been seeing over and over and over again on this review, the law of sines and the law of cosines can be used to find the unknown parts. Discuss the specific circumstances for using each law. And in a nutshell, I know the rule. If I have 2 angles or I have side-side angle, I'm going to use law of sines. And be aware of the situation with side-side angle. Anything else, I'm going to use law of cosines. So there it is right there. 2 angles or a side-side angle implies law of sines. But don't forget, side-side angle implies we could have 0 triangles, 1 triangle, or 2 triangles. All right. Anything else? Law of cosines. Okay. Now, let's get into the chapter 10 stuff. Simplify cosine of 75 degrees times cosine of 15 degrees plus sine of 75 degrees times sine of 15 degrees. Well, that looks like the cosine of alpha plus or minus beta identity right there. So here it is right here. And notice I saw the cos, so I'm thinking cosine right here, all right? And remember your rule right here, okay? Let's see, cosine of alpha times cosine of beta. This is a plus or minus, this is a minus plus. So that's really simple then. Let's set this up. So we're going from the right-hand side to the left-hand side. So I'm going to say cosine of, and my angles are 75 and 15. And remember, this is a plus, meaning this is a minus. And you see that in the notation right here. All right. If I have a plus over here, I've got to have a minus there between my 2 angles. And isn't 75 minus 15 just 60 degrees? So that's cosine of 60 degrees. And that's one of our key angles, and we know this without a calculator. Cosine of 60 degrees, well, let's highlight the terminal ray for a 60-degree angle in standard position. There it is right there. And cosine would be this horizontal distance right there, which is 1/2. And there you have it. Okay, number 2. Same scenario, except this time we have the sine of alpha plus or minus beta. And I see that immediately by my first term of sine times cosine. So there it is right there. So we're going to go from the right to the left again. So that's going to equal a sine of, and what are my 2 angles right there? They are 75 and 15 degrees right here. And now note the plus right here. And note the rule here, plus minus, plus minus. So I see a plus and a plus. The sign remains the same right there. So if this is a plus, I've got to add the alpha and the beta right there. And that becomes sine of 90 degrees. And you guys don't even need to look at a picture right now. You all know sine of 90 degrees is 1. But let's visualize it. Here's my terminal ray for 90 degrees right there. And that vertical distance on the unit circle is exactly 1 unit. So sine of 75 degrees, cosine of 15 degrees, plus cosine of 75 degrees, sine of 15 degrees becomes 1. All right, number 3. Oh, look at this. So we're going to have to apply cosine of alpha plus beta, and then plus and do a cosine of alpha minus beta. All right, so let's do this. So again, cosine of alpha plus or minus beta, right there, right? So we're going to take this, and we're going to start with our cosine of 30, and then we're going to go cosine of our x, and now we have a plus right here, don't we? But look at this, alpha plus or minus beta, and then we got a minus plus over here. So that plus, you look right here. If I have a plus here, I've got to have a minus right there. So let's put a minus in. And then we go sine of 30 and sine of x. All right, so that's this first term right there. Now plus, and now we're going to go cosine of the 30, cosine of the x, and you see the minus here? That means we're going to end up with a plus right here. Okay, and now let's go sine of 30 and sine of x. Now, some people like to simplify this by doing our trigonometry first. Some people like to combine like terms. So this one, let's go ahead and do the trigonometry right now. What is cosine of 30 degrees? Well, cosine of 30, here's your 30 degree right there. And cosine of that angle is this horizontal distance right here, which you guys should see as a root 3 over 2. And then cosine of x minus, and sine of that 30 degree, that's that vertical distance right there, which is that 1/2. And then sine of x plus, and then we've got our cosine of 30 degrees again, it's still root 3 over 2. And our cosine of x, and then a plus, and our sine of 30 degrees is still 1/2, and then sine of x. Now, let's combine our like terms now. All right, so let's see. Do you see the negative 1/2 sine of x and the positive 1/2 sine of x? Those would cancel. And then I have root 3 over 2 cosine of x plus root 3 over 2 cosine of x. If I combine those, I've got root 3 cosine of x. So there it is. Very cool. All right, number 4. Same type of problem. So let's go with sine of alpha plus or minus beta. Right down there. All right, so now with the sine, we're going to start with the sine of 45 degrees. And now we're going to go cosine of the x. And do you see the minus right here? And the sign remains the same. Okay, we're going to have a minus right here. And that is because if I have alpha minus beta, I've got the minus there. And then we're going to go cosine of 45 degrees and sine of x. Okay, that's that first term. Now here's my minus. And notice I went minus and then I did brackets because I'm going to have to put this within the brackets, so I'm sure I distribute that minus to each term inside. So sine of 45 degrees plus x, that would be a sine of 45, a cosine of x, and do you see the plus? The sign remains the same. I'm going to end up with a plus right there. All right, and then we go cosine of 45 degrees and the sine of x. All right, now on the last problem, we simplified our terms or our factors that had trigonometry. All right, let's combine like terms first this time. Okay, because look what you got right here. Sine of 45 cosine of x minus sine of 45 cosine of x. Those would cancel. All right, and then I can combine to get negative cosine of 45 degrees sine of x and another negative, don't forget to distribute that negative, cosine of 45 degrees sine of x, which is negative 2 cosine of 45 degrees sine of x. And now I just need to find cosine of 45 degrees. And of course, cosine of 45 degrees, isn't that a root 2 over 2? Let's visualize it. Here's my 45 degrees, and this horizontal distance right here is exactly root 2 over 2. You notice how they wrote the x-coordinate as 1 over root 2? They did not rationalize the divisor like we do, but we're going to call that a root 2 over 2. And with that, then, we can easily cancel. So the 2's cancel there, and I'm seeing a negative root 2 sine of x. Okay, number 4. Number 5. Find the exact value of cosine of 15 degrees. Well, you guys, I don't know cosine of 15 degrees, but are there 2 key angles in the first quadrant of the unit circle that I could add or subtract and get 15 degrees? I think so. So we're going to use our cosine of alpha plus or minus beta right there. All right. And I'm thinking cosine of, now what 2 angles can I add or subtract to get 15? Could I use the 40 or the 45 and the 30? Yeah. So I'm going to go 45 minus 30. All right. Then I can use this identity right there. All right. So let's go. Cosine of 45 degrees, cosine of 30, and you guys see the minus here. That means I've got a plus right here. All right, and then let's go sine of 45 degrees, and sine of 30 degrees. Okay, I'm sorry, I'm getting tired, you guys. All right, so that's that. Let's do our trigonometry now. What is cosine of 45 degrees? Yeah, here's my 45 degree terminal ray right here. And that cosine is still root 2 over 2. Okay, cosine of 30 degrees. Well, that's this terminal ray right here. And that distance would be a root 3 over 2. Okay, and then we got a plus. And sine of 45 degrees, well, this vertical distance right there is root 2 over 2. And sine of 30 degrees, well, this vertical distance right here would be a 1/2. Now let's simplify this for our exact answer. So do you all see a common denominator of 2 times 2, or 4? And then what's the first term up top? Root 2 times root 3 is a root 6, plus root 2 times 1 is a root 2. So the exact answer of cosine of 15 degrees is root 6 plus root 2 divided by 4. And we'd leave it just like that, because if we punch that out, we would get an irrational number. And that we would have to round, and they asked us for an exact answer. All right, number 6. This is our final identity other than the angle formed by the intersection of 2 lines. All right, so right here, when I see this, find tangent of, you know what I'm thinking right now? Alpha minus beta. So let's do our identity. Tangent of alpha plus or minus beta would be tangent of alpha and plus or minus. I put a plus or minus right there. Tangent of beta. And then I go 1, and then I go minus plus here. Tangent of alpha, tangent of beta. All right. So let's see. I probably put these in directly before I simplified anything. All right. So I'm picturing tangent of alpha becomes tangent of 5 pi over 4. And this is a minus, meaning I need a minus right there. And then I have the tangent of the theta, okay, over 1, and this minus means this is a plus, tangent of 5 pi over 4, times tangent of theta. There it is, step 1. Now, what's tangent of 5 pi over 4? Well, let's take a look at our unit circle. 5 pi over 4. 1, 2, 3, 4. That'd be right here in quadrant 3. All right. And tangent is sine over cosine. All right. Which would be, the sine is going to be a negative root 2 over 2. And the cosine is also going to be a negative root 2 over 2. So that's going to be, well, oh, looks like right now I'm not simplifying that yet. I'm just putting in tangent of 5 pi over 4. That's going to be a 1, you guys. Minus tangent of theta minus negative 1/3 or plus 1/3. Okay, and then 1 plus. All right, and tangent of 5 pi over 4 is still 1, and tangent of theta is still given as negative 1/3. Now let's do the arithmetic, and we are done. So 1 plus 1/3, that's going to be a 4/3, and that's 1 minus 1/3, that's 2/3, equals, and my divisors of 3 would cancel, leaving me 4 over 2, which is 2. So tangent of 5 pi over 4 minus theta is 2, as long as tangent of theta equals negative 1/3. Number 7. Wow, looks like the same type of problem. Oh, this is almost a proof though. We're going to show that with the given information, we're going to show that tangent of alpha plus beta has to equal tangent of pi minus beta. Wow. All right. Well, let's simplify these independently of each other and see if we get the same answer on both sides using our identity for tangent of alpha plus or minus beta. So on the left, I'm going to have a tangent of alpha, which they gave me tangent of alpha is 4/3. All right. And I have a plus, so I need a plus there. All right. And then tangent of beta, which is that negative 1/2. Okay. Over 1. And then I have a minus here. Note the plus minus, the minus plus, some minus. All right. And then tangent of alpha times tangent of beta, or 4/3 times negative 1/2. Okay, that's my first step on the left. Let's do the first step on the right now. Okay, and we'll simplify these a little bit. So here I get, with tangent of alpha minus beta, I get tangent of pi. Well, where's pi? Right there. And tangent is sine over cosine. Well, sine of pi is 0, so that's just a 0. Okay, minus tangent of beta, which is still that negative 1/2. All right, and then we got 1 and a plus, and then we have our tangent of pi, which is still 0, times the tangent of beta, which is still negative 1/2. All right, let's go to the next step. Let's simplify the left-hand side. That would be 4/3 minus 1/2. Well, common denominator would be 6, so that'd be 8 over 6 minus 3 over 6. Let's make sure we got this right, because I'm getting tired. Yeah, 8 over 6 minus 3 over 6. So that's going to be 5 over 6. And then here I've got a 1 plus 4 over 6. That's a 10 over 6. Okay, let's simplify this side now. Well, that's 1/2 over 1. That's just 1/2. Okay, cool. Now I'm hoping this simplifies to 1/2 and we are done. Well, 5 over 6 over 10 over 6, the 6's would cancel right there. And we have 5 over 10, which reduces to 1/2. And 1/2 equals 1/2. We could say quad erat demonstrandum. Okay, now this is our last concept. Find the angles formed by the intersection of y equals 2x plus 1 and y equals 4 minus 3x. All right. Now, you don't need to graph these. You can answer these without the graphs, but I usually like to do the visual and see it. So what we're doing here is we have tangent of theta equals, now remember this rule, we created this rule ourselves. We have the slope of the first line minus the slope of the second line over 1 plus the product of those two slopes. There you go. So it looks like I did not even draw a picture. All right. So anyway, what is the difference between these two slopes, and which one you call the first or the second really doesn't matter. I see a slope of 2 and a slope of -3. 2 minus -3 would be 2 plus 3. This is going to end up being a 5 right there. Okay, and there you go. And then 1 plus, and the product of those two slopes would be 2 times -3, -6. So that's 1 plus -6, or 1 minus 6. All right, and I see a 5 over -5, which is -1. So when does tangent have an output of -1? All right, you're going to go then. Now, if you do this on your calculator, you'd get rid of the tangent with an inverse tangent, and your calculator is going to give you a negative answer. All right. Now, if you don't use the calculator, you don't have to worry about that. But what I see, tangent has an output of -1 in quadrant 4 with this angle right there. And your calculator would give you that -45 degrees right there. All right. Which the intersection of these two lines is not going to give me a negative angle. So I need to know in what other quadrant is tangent positive. And that would be quadrant 2. Okay. right here, or excuse me, where tangent is negative. Okay, right there, that angle right there, and that is going to be what, 135 degrees? So our obtuse angle right there would be 135 degrees. And then this angle and this angle form a straight angle, so that they would have to add up to 180, so that makes this one a 45-degree angle. And there you go. There's the two angles formed by the intersection of those two lines. All right, last problem. Suppose angle A is acute and cosine of A equals 4/5. Well, I'm going to use some right triangle trigonometry right here. So if angle A is acute, I'm going to draw a quadrant 1 right triangle with my angle A being my acute angle. And if cosine of A is 4/5, so SOHCAHTOA, isn't the adjacent to A going to be the 4? And the hypotenuse of my triangle the 5? And then isn't this a Pythagorean triple? This is not the scale, but wouldn't this leg then have to be a 3? And if you don't remember your Pythagorean triples, you could find that with Pythagorean theorem. All right, and then what they ask us? Well, what's sine of A? Well, I see it right there in my picture. Sine of A is SOHCAHTOA. Sine is opposite to hypotenuse, so that's going to be a 3/5. All right, I hope you guys enjoyed the review presentation online here. And I'm sorry, but my allergies are acting up a little bit, so I was doing a little bit of sneezing and my nose is kind of stuffed up. But I hope I powered through it, and if you guys have any questions, please get a hold of me. You guys have a great day.